Now, we said that a moving object has the ability to do work. So this was our definition of kinetic energy. So recall, kinetic energy was the ability for a moving object to be used to do work. So what that meant was, again, if I took this eraser and I dropped it, by this thing moving and then slamming into something, we could use that to then do work. Now, this so far was only true for an object moving in a straight line. Now the question is, can a rotating object such as this do work? Does this have an ability to do work by rotation? Meaning, does this thing have a rotational kinetic energy to it? Well, one way we can convince ourselves that yes, this thing has the ability to do work is imagine I put a hammer on here. Actually, I do have a hammer. So let's say I staple this hammer or glue it onto here, so could I use this thing to do work? Well, yes. If I took this thing and I simply rotate, we can use the rotation of this object to do work. So, since this thing, by simply rotating, not moving in translational sense, but simply rotating, has the ability to do work, this thing then has to have what we call rotational kinetic energy. So let's talk about rotational kinetic energy. So what is rotational kinetic energy? So rotational kinetic energy is the ability of a moving object to do work. Exactly the same thing as kinetic energy, where by changing its kinetic energy, its translational kinetic energy, in this case by changing its translational kinetic energy or its rotational kinetic energy, we can actually do work. So let's talk about how that happens. So let's say I have an object such as this wheel, and this thing is rotating about its center axis. So say here, this thing is rotating about this point, let's say in this direction with an angular velocity of omega. So what I want to know then is how much kinetic energy is contained within inside of this object. So what is the ability for this thing to actually do work? So let's do this by simply chopping this thing up to a bunch of small pieces. So same thing we did with the center of mass. Let's say we're going to look at this part here. So this thing has a small mass, delta m1. Got this one up here. This thing has a mass of delta m2. This thing then has a mass of delta m3, and etc. Now, each one of these has their own position vectors then. So this is going to have a position vector from here to here. So this is going to be R1. This is going to have its own position vector, R2. This one's going to have its own position vector, R3. Now, as we know from rotation back in chapter 4, we know is since this thing is rotating, every point along this axis, or any point for that matter, all has to have exactly the same rotational speed. Which means if I looked at a small section here, as this thing is rotating in this direction, this is also rotating with exactly the same angular velocity, and so is this point down here. But what we also know is that this point up here, since it's further away from the axis, it has to be moving with a greater translational velocity, or that tangential velocity, as opposed to a point down here, since it's not as far away, it doesn't have to move as fast to make sure this thing stays together as a rigid body. So what that tells us then is that each one of these objects then, each one of these masses, are moving first tangentially to the circle with their own velocity. So this is going to have a velocity v1, this is going to have a velocity of v2, this one's going to have its own velocity of v3. So we can say then is what, even though this thing is rotating, if we imagine we take a snapshot at a given moment of time, so a picture of it, each one of these masses that we have now cut has their own translational kinetic energy at this given moment. So we know is this one has a translational kinetic energy in this direction, this one has a translational kinetic energy in this direction, this one has a translational kinetic energy in this direction. So the total kinetic energy this thing has is simply the sum over all of these individual kinetic energies. So we can then say that what the rotational kinetic energy of this object is simply equal to the sum over all the individual translational kinetic energies. Well, we're going to turn this into rotational in just a second. Now, we know by definition that the translational kinetic energy then is simply equal to 1/2 times the mass of the object, so in this case r delta m I, times the velocity at which it is moving squared. Or in this case, the speed squared. Now, going back to what we talked about in rotational, what we know is that the tangential velocity that this thing has, or the translational velocity, is related to the angular velocity by simply the radius. So going back to chapter 4, we know is that the velocity that each one of these has is equal to the angular velocity weighted by the distance at which it is away. So again, the further it is away, that means the more translational velocity it has to make sure that it stays, in this case, within the circle. So let's replace each one of those. So this is simply going to become equal to 1/2 times the sum over I of then delta mi times ri squared times then the angular velocity squared. Now, this thing here, we're going to call a new variable, and this is what we're going to call I. So this thing goes as 1/2 I times omega squared, where I here is what's known as the moment of inertia. We'll talk about what that is in just a second. So in this case, what this says then is that the moment of inertia is then equal to the sum over each individual mass that we chop this thing up into times the distance squared at which this thing is at. Now, this is only true for discrete objects. But again, if I was dealing with something like the ruler here, or something like the hammer, or even this wheel, these would all be considered then continuous objects. So in this case, we would do the same thing as before. We would take the limit as each one of these delta mi's goes to 0, meaning that these are going to become differential again. In this case, we have the limit of a sum, and again, the limit of a sum we know is a Riemann sum, which is the same thing as an integral. So this is going to become equal to the integral of the position squared integrated over the differential mass. Now again, same thing as with center of mass. Integrating over the differential mass doesn't really quite make any sense. So again, what we're going to do is we're going to turn this into a geometry integral. So we're going to rewrite dm in one of those 3 ways that we did before, which again means that dm is going to be either equal to lambda dl, a to dA, or rho dv, depending on the geometry of the problem. Now, let's compare. So let's talk about that replacement stuff that we talked about earlier in the semester back in chapter 4. So first of all, let's remind ourselves that the translational kinetic energy that an object has is simply equal to 1/2 mv squared. Now, if we think about our replacement chart that we had before, we said that x goes to theta, v goes to omega, a goes to alpha, which means that if I compare this to this, the 1/2 are the same. The velocity then is the same, at least in its angular counterpart, which means that m, the mass, is equivalent then to I, this moment of inertia. So in our replacement scheme, this means then that mass is going to be re-identified as this object at moment of inertia. So good. So let's use this to now talk about what is moment of inertia. Now, when we talk about forces, a long time ago, what we said is that mass is what's also known as the inertial mass, which is a resistance or measure of resistance of an object has to acceleration. Which again means that what? If I applied a force onto an object such as this table, with a certain amount of force, if I apply it to this thing, I can accelerate it at a particular rate. But as I start adding more and more mass to it, so I start putting all these different objects on top of it, what happens in this case then is with that same amount of force at which I'm applying, this thing then is going to accelerate much slower because the mass has now increased. This came from Newton's second law. Now, what this is saying then is that this idea of moment of inertia then has the same conceptual idea as that of mass. So this is what we can call rotational mass, or usually what's known as rotational inertia or moment of inertia. So since mass is a resistance of an object to linear acceleration, moment of inertia then is the measure of an object's resistance to a rotational acceleration, i.e. an angular acceleration. Now, by looking at the structure of it, this thing is now dependent not only on the mass itself, but how that mass is actually distributed. Which basically means that what? By me rotating this ruler, for example, around different points, the way it's going to rotate, or the resistance that this thing has to rotation, will change. So basically meaning if I was rotating this thing about the center of mass, That's a lot easier for me to rotate it this way as opposed to trying to rotate it about this endpoint, because now the mass is being distributed in a different way. So because this thing goes as the radius squared, what that means is that now, when these things are a certain distance away, which in this case is 50 centimeters, that 50 centimeters squared is now much smaller than when I'm trying to rotate it out here at 100 centimeters, because now that 100 centimeters squared is now a much bigger quantity. So as I try to rotate something around, how I rotate it around, or about what axis I'm rotating this thing about, will change the properties of how this thing is rotating. Which again means it's going to become more or less resistant to rotation the bigger the object is, or at least where I'm rotating this thing about. So this quantity of the moment of inertia will have to be recalculated every time we rotate an object about some sort of different point. Now, but ultimately, all this thing says then is that the structure of this translational or rotational kinetic energy stay exactly the same. So again, translational kinetic energy is 1/2 the mass times the velocity squared, where the rotational kinetic energy is 1/2 times the angular equivalent of mass, which is the moment of inertia, times then the angular equivalent of velocity, which is the angular velocity squared. So structurally wise, they're exactly the same thing, but again, physically they're slightly different. So again, kinetic energy, or at least translational kinetic energy, is how much work can I get out of this thing moving in a straight line. Rotational kinetic energy then is how much work can I get out of this thing simply rotating. The faster I make this thing rotate angularly, the more amount of kinetic energy I'm going to get. Or if I change the axis from this thing rotating about the center axis to rotating that about this point, I'm going to get more kinetic energy out of it because I have now increased the moment of inertia. But again, structurally wise, these two things are identically the same.